What if I told you there's an invisible force in the universe so powerful it can rip stars apart, warp the fabric of space itself, and even freeze time? This isn't science fiction, it's the reality of gravity at its most extreme. Out there in the cosmos, beyond the safety of our little blue planet, gravitational forces operate on scales so mind-bending, they defy everything we think we know about the laws of physics. Picture a place where a single teaspoon of matter weighs as much as a mountain, where light itself can't escape, and where the very rules of reality seem to break down. These aren't just theories scribbled on a chalkboard, they're real, observable phenomena happening right now in the darkest corners of the universe. Gravity is the quiet architect of the cosmos, the unseen hand that sculpts galaxies, guides planets, and dictates the fate of stars. But when gravity is pushed to its limits, it becomes something far more dramatic, a cosmic monster capable of unimaginable destruction and creation. From the crushing depths of neutron stars to the bottomless pits of black holes, the universe is filled with gravitational extremes that challenge our understanding of existence. And here's the wildest part: these forces aren't rare anomalies. They're everywhere, shaping the universe in ways we're only beginning to unravel. So buckle up, because we're about to take a journey into the heart of these gravitational extremes. We'll explore how a black hole's pull can stretch you like spaghetti, why some stars are so dense they bend light into impossible shapes, and what happens when two cosmic giants collide in a gravitational showdown that shakes the fabric of space-time. This isn't just a tour of the universe's most violent forces, it's a glimpse into the very machinery of reality. And by the end, you'll never look at gravity the same way again. Ready to dive in? Let's go. Imagine a star 20 times more massive than our Sun collapsing under its own weight, crushing down with such unimaginable force that it punches a hole straight through the fabric of space-time. This is how a black hole is born. At its core lies the singularity, a point of infinite density where gravity becomes so powerful, the laws of physics as we know them simply stop working. Around it, the event horizon acts like a cosmic point of no return. Cross that boundary, and there's no coming back, not even for light, the fastest thing in the universe. That's why black holes appear utterly black. They swallow every photon that dares to venture too close, but their appetite doesn't stop there. Black holes act as the universe's ultimate vacuum cleaners, devouring anything unlucky enough to drift into their gravitational grip. Gas, dust, even entire stars, they're all torn apart and stretched into thin streams of matter in a process so violent, scientists call it spaghettification. Picture this: if you fell feet first toward a black hole, the pull on your toes would be so much stronger than on your head that your body would stretch like taffy until you were nothing more than a strand of atoms swirling into the abyss. And yet, for all their destructive power, black holes aren't just cosmic wrecking balls. They're also crucial architects of galaxies. Supermassive black holes, millions or even billions of times heavier than our Sun, lurk at the centers of most galaxies, including our own Milky Way. Their gravity shapes the orbits of stars, funnels matter into swirling disks of superheated plasma, and sometimes even powers the brightest objects in the universe, quasars, which outshine entire galaxies. Without black holes, the universe as we know it wouldn't exist. They're monsters, yes, but monsters that keep the cosmos in balance. If black holes are the universe's ultimate vacuum cleaners, then neutron stars are nature's most outrageous crushing machines. These cosmic leftovers form when a massive star explodes in a supernova but isn't quite heavy enough to collapse into a black hole. What remains is perhaps the strangest object in the universe, a star corpse so dense that just a sugar cube-sized piece of it would weigh as much as all of humanity combined. We're talking about squeezing 1.5 times the mass of our Sun into a sphere no wider than Manhattan. That's like cramming Mount Everest into a coffee mug. The gravity on the surface of a neutron star is so unimaginably strong, it would flatten you into a single atom thick before you could blink. Here's where things get even wilder. That insane density does bizarre things to matter itself. Under normal circumstances, atoms are mostly empty space, tiny nuclei with electrons whizzing around them like planets orbiting a star. But on a neutron star, gravity wins. It smashes protons and electrons together so violently that they merge into neutrons, creating an ocean of pure nuclear matter with no empty space left. It's like taking every skyscraper on Earth and compacting them into a single brick. And the surface, forget about walking, you'd be vaporized instantly by temperatures exceeding 1 million degrees. But the real showstopper comes when neutron stars spin. Some rotate hundreds of times per second, becoming cosmic lighthouses that blast beams of radiation across the galaxy. These pulsars keep time more accurately than atomic clocks, with flashes so regular you could set your watch by them from thousands of light years away. There are even ones called magnetars, with magnetic fields so strong they could erase your credit cards from halfway across the solar system. Yet for all their terrifying power, neutron stars might hold the key to understanding how gold, platinum, and other heavy elements are born. When two neutron stars collide, the explosion showers space with these precious metals in a glittering cosmic fireworks display. That stunning gold necklace you're wearing. It was likely forged in the heart of a neutron star collision billions of years ago. Spaghettification might sound like a silly word, but it describes one of the most horrifying ways the universe can kill you. Picture this: you're floating toward a black hole, feet first. At first, everything seems normal until you cross the point where gravity's pull on your toes becomes unimaginably stronger than on your head. What happens next is like the worst tug of war imaginable. Your body stretches, elongating thinner and thinner as if you were made of taffy. Your limbs, your torso, even your bones, all of it gets pulled into a noodle-like strand, atom by atom, until you're nothing more than a stream of particles spiraling into the void. This nightmare scenario isn't just theoretical. It's the brutal reality of tidal forces near a black hole. Gravity isn't uniform. The closer you are to the source, the stronger its grip. Near a black hole's event horizon, that difference becomes extreme. Just a few feet can mean the difference between a survivable pull and a force so strong it overcomes the very bonds holding your molecules together. It's like being caught in an ocean tide, except instead of water, it's the fabric of space itself stretching you apart. And it's not just unlucky astronauts who face this fate. Stars, planets, even clouds of gas, anything that ventures too close suffers the same spaghetti-like demise. Astronomers have actually watched this happen in real time. In 2019, telescopes caught a star being shredded by a supermassive black hole 21 million light-years away. Over months, the star was torn into a glowing ribbon of plasma, swirling into oblivion like water down a drain. That's the terrifying power of spaghettification. It's not quick, it's not clean, and there's no escape once the process begins. But here's the strangest part: from your perspective, falling in, you might not even realize it's happening. Thanks to the warping of space-time, time itself slows down near a black hole. What looks like a slow, agonizing death to outside observers could feel like seconds for you, right up until the moment you're reduced to atoms. It's a paradox that shows just how extreme gravity can twist reality itself. This gruesome process isn't just cosmic horror, it's a critical clue for scientists. By studying how matter behaves during spaghettification, we learn about the nature of black holes, the limits of Einstein's theories, and even the fundamental forces that govern the universe. Every stretched star, every spiraling strand of gas is a message written in gravity's brutal handwriting, and we're just beginning to decode it. Einstein was right again. A century after he predicted them, scientists finally detected the faint shudders of gravitational waves rippling through the cosmos. These aren't just any waves. They're distortions in the very fabric of space-time itself, created by the most violent events in the universe. Picture tossing a pebble into a pond, the ripples spread outward, bending the water's surface. Now imagine that pebble is two black holes, each weighing dozens of times more than our Sun, spinning around each other at nearly the speed of light before colliding in a cataclysmic merger. The impact sends shockwaves through space-time so powerful, they stretch and squeeze everything in their path, including Earth itself. We only caught these whispers from the cosmos thanks to one of humanity's most astonishing experiments, LIGO, the Laser Interferometer Gravitational Wave Observatory. Its twin detectors, separated by thousands of miles, act like cosmic microphones. Each houses lasers bouncing down 4-kilometer-long tunnels, perfectly aligned to detect changes tinier than 1/10,000th the width of a proton. When a gravitational wave passes through, it subtly alters the length of these tunnels, making the lasers fall out of sync. That's how, in 2015, scientists heard their first chirp, the sound of two black holes merging 1.3 billion light-years away. But why does this matter? Because gravitational waves are like a whole new sense for astronomy. Before them, we could only study the universe by observing light, visible X-rays, radio waves. Now we can hear it. These ripples carry secrets about their origins untouched by the distortions that affect light, giving us a pristine record of events too violent to see. Take neutron star collisions. When two of these ultra-dense corpses spiral together, they don't just send out gravitational waves, they also forge gold, platinum, and other heavy elements in a fiery explosion called a kilonova. The first time LIGO spotted one of these mergers in 2017, telescopes around the world swiveled to watch the aftermath. The data confirmed something extraordinary. Gravitational waves travel at the speed of light, just as Einstein's equations suggested. But they also revealed something unexpected. The collision spewed out enough gold to outweigh our entire planet. Every piece of jewelry on Earth likely contains atoms born in such a cataclysm. What's truly mind-bending is how delicate these detections are. By the time gravitational waves reach us, they've weakened so much that the distortions they cause are smaller than an atom. Yet somehow we've built machines sensitive enough to catch them. It's like detecting a single grain of sand dropped on the other side of the galaxy. And this is just the beginning. New observatories like Europe's planned Einstein telescope will listen for waves from the earliest moments after the Big Bang, potentially uncovering how the universe itself began. At the heart of nearly every major galaxy, including our own Milky Way, sits a silent predator, a supermassive black hole with an appetite so vast it shapes the destiny of everything around it. These aren't just oversized versions of their stellar mass cousins. They're galactic-scale monsters weighing millions or even billions of times more than our Sun, with gravitational pulls so overwhelming they dictate the dance of entire galaxies. Picture a cosmic puppet master, invisible strings tugging at thousands of stars, forcing them into orbits that reveal its presence through motion alone. Take Sagittarius, a star, the behemoth at the center of our galaxy. Though it's 4 million times the mass of the Sun, it fits within a space smaller than Mercury's orbit. That concentration of mass creates gravity so intense, nearby stars whip around it at thousands of kilometers per second, some completing wild, looping orbits in just a few Earth years. Astronomers have tracked one star called S2 as it makes this frenzied journey, reaching speeds over 15,000 miles per second at its closest approach. That's 2.5% the speed of light, all because of an object we can't even see. But here's where it gets stranger. These black holes don't just sit there passively. When they feed, they become the most powerful engines in the universe. Gas and dust spiraling into them form superheated disks that glow brighter than all the stars in their host galaxies combined. Some launch jets of particles at nearly light speed, stretching tens of thousands of light years across space. These jets can sterilize entire swaths of galaxies, preventing star formation by blasting away the raw materials needed to make new suns. Yet paradoxically, supermassive black holes might also be essential for life. Their gravity likely helped form the dense galactic cores where early stars clustered, creating stable environments for planets to emerge. Some theories suggest that without these gravitational anchors, galaxies might never have taken their familiar shapes. Spiral arms wouldn't wind so tightly, and stars might have scattered into the cosmic void. The most mind-bending realization: these black holes grow in lockstep with their galaxies. The larger the galaxy, the more massive its central black hole, as if some unseen cosmic rule connects them across billions of years. It's a relationship we're still deciphering, one that hints at black holes not as destroyers but as architects, sculpting the universe on scales we're only beginning to comprehend. Here's something that will bend your mind more than a black hole bends space. Gravity doesn't just pull on objects, it pulls on time itself. Near a massive object like a black hole, time doesn't flow the way it does here on Earth. It slows down, warped by gravity's relentless grip. Imagine two identical clocks, one placed on Earth, the other drifting near a black hole's event horizon. The clock near the black hole would tick noticeably slower, as if time itself were dragging its feet. This isn't science fiction. It's confirmed physics, proven by experiments so precise they could measure time differences between your head and your feet. The deeper you sink into a gravitational well, the more extreme the effect becomes. Near the surface of a neutron star, where gravity is billions of times stronger than Earth's, time crawls at a fraction of its normal speed. And at the edge of a black hole, time nearly stops. From an outside observer's perspective, someone falling toward a black hole would appear to move in slow motion, freezing just before crossing the event horizon. For the person falling in, though, their own clock would seem normal, but the entire universe outside would speed up, stars aging and galaxies evolving in what felt like moments. Einstein called this phenomenon gravitational time dilation, and it's baked into the very fabric of his theory of general relativity. The closer you are to a massive object, the more space-time curves, and the slower time passes compared to areas with weaker gravity. Even here on Earth, the effect is measurable, just incredibly tiny. A clock at sea level, where Earth's gravity is slightly stronger, ticks slower than one on a mountaintop by about 1 second every 30 million years. GPS satellites have to account for this, adjusting their onboard clocks to stay synchronized with ground stations. If they didn't, your navigation would be off by miles within minutes. But near a black hole, the effect becomes grotesquely magnified. Picture a dying star collapsing into one. As it nears the event horizon, light from its surface takes longer and longer to escape the gravitational well, stretching into deeper reds until it vanishes entirely. To a distant observer, the star's final moments stretch into eternity, frozen in time like a photograph. Meanwhile, for the star itself, time races forward and collapse happens in an instant. This bizarre disconnect isn't a glitch, it's a fundamental feature of how gravity and time intertwine. The wildest implication: if you could orbit just outside a black hole's event horizon and survive the tidal forces, you could experience time travel into the future. A few hours for you might be decades or centuries for everyone else. It's a one-way trip with no return ticket, but it proves something astonishing. Gravity doesn't just shape space. It sculpts time itself, turning the universe into a cosmic clock where no two ticks are ever quite the same. Black holes might be the universe's ultimate one-way streets, but what if gravity had an exit door? Enter white holes, theoretical cosmic mirrors to black holes, where the rules of gravity flip inside out. Picture a black hole in reverse. Instead of pulling everything in with unstoppable force, a white hole violently repels matter and energy, blasting it outward like a cosmic fire hose set to maximum. Nothing can enter a white hole, not light, not spacecraft, not even a single atom. the event horizon becomes an impenetrable barrier, but this time it's pushing everything away with equal ferocity. The idea isn't just science fiction. White holes emerge naturally from the same equations that predict black holes in Einstein's theory of general relativity. They're mathematically possible, but whether they exist in reality is one of physics' greatest unanswered questions. Some scientists think they could be the other end of a black hole's tunnel, a hypothetical bridge through space-time called an Einstein-Rosen wormhole. If that's true, falling into a black hole might not mean certain doom. You could theoretically pop out of a white hole somewhere else in the universe, like a cosmic subway system with no return tickets. Here's the catch: white holes defy everything we know about thermodynamics. While black holes obediently follow the universe's trend toward disorder, white holes would essentially reverse entropy, spitting out pristine energy in a way that seems to magically reorganize chaos. That's why most physicists suspect they're mathematical curiosities rather than real objects, like finding a solution to an equation that describes a car moving backward in time. The universe appears allergic to such violations of cause and effect, yet nature has surprised us before. Some researchers speculate that the Big Bang itself might have behaved like a white hole, erupting concentrated energy into the fledgling universe. Others suggest that tiny, quantum white holes could explain mysterious high-energy cosmic rays or even dark matter. And if white holes do exist, they'd be nearly impossible to spot. Their defining feature is repelling everything, including the light that would let us see them. The beauty of white holes lies in their paradox. They challenge us to rethink gravity's limits, to imagine a cosmos where the rules we take for granted can invert. Whether they are hidden in distant galaxies or confined to chalkboard equations, they remind us that the universe still holds mysteries no one has yet dreamed of, places where gravity doesn't just bend space but rewrites the script entirely. Gravity doesn't just pull, it bends. One of its most jaw-dropping tricks is turning massive objects into cosmic magnifying glasses, warping the very fabric of space so dramatically that light itself has to curve around them. This phenomenon, called gravitational lensing, is nature's ultimate telescope, letting us peek at galaxies so distant they should be invisible. Think of space as a vast rubber sheet, with galaxies and clusters creating deep dimples where they sit. When light from a faraway object travels toward us, passing near one of these dimples, it doesn't move in a straight line. It follows the curve like a marble rolling around the edge of a bowl. The result, the background object appears distorted, stretched into arcs, or even multiplied into eerie mirror images. Sometimes entire galaxies get smeared into glowing rings around the foreground mass, like a celestial halo. Einstein predicted this effect over a century ago, but even he doubted we'd ever witness it. Today, it's one of astronomy's most powerful tools. Take the Hubble Space Telescope's deep field images. Many of those faint, ancient galaxies weren't spotted directly. Their light was amplified by colossal galaxy clusters acting as natural lenses, boosting signals too weak to detect otherwise. It's like finding a hidden message by holding a magnifying glass over faded ink, except the ink is a 10-billion-year-old galaxy, and the magnifying glass is a trillion-sun gravitational trap. The most extreme cases look like something from a sci-fi movie. Galaxy cluster Able 618, for instance, distorts space so severely that a single background galaxy appears replicated into at least 12 separate images arranged in a ghostly cross pattern. Other lenses create Einstein rings, near-perfect circles of light where a distant galaxy's image gets warped into a glowing loop around the lensing mass. These aren't just cosmic curiosities, they're precision instruments. By measuring how much the light bends, scientists can weigh the lensing object even when it's invisible. That's how we first mapped dark matter, uncovering the hidden scaffolding of the universe. But the real magic happens when lensing reveals the unreachable. Some of the youngest galaxies ever observed, infant star systems born when the universe was just a fraction of its current age, only became visible because their light got a gravitational boost on its 13 billion-year journey to us. Without these natural telescopes, their whispers would have been lost in the cosmic static, and the implications go even deeper. Certain lenses act like zoom filters, letting us study details in distant galaxies that should be impossible to resolve. Imagine reading a newspaper headline from a mile away. That's the level of magnification gravity provides. Astronomers have used this to spot embryonic star clusters in far-off galaxies, track individual supernovae in unprecedented detail, and even test whether Einstein's theory of gravity holds true across the vastness of space and time. What's truly wild is that this cosmic quirk doesn't just show us more of the universe, it lets us see it differently. A single lensing cluster can reveal dozens of background galaxies at once, all at different distances, like flipping through layers of cosmic history in a single glance. It's as if gravity itself is handing us a time machine, bending not just light, but our understanding of how the universe grew up. Most black holes sit anchored at the centers of galaxies like cosmic spiders in a web, but not all of them. Some break free, becoming lone wanderers of the interstellar void. These rogue black holes drift through galaxies like invisible ghosts, their presence betraying them only when it's too late for anything caught in their path. Picture a stealth predator 10 times heavier than our Sun, moving silently through the darkness at hundreds of thousands of miles per hour, no glowing accretion disk, no swirling vortex of doomed gas. Just pure, naked gravity, waiting to ambush anything that strays too close. The way these renegades form is just as violent as their nature. When galaxies collide, their central supermassive black holes often engage in a gravitational dance, spiraling toward each other until they merge. But sometimes, the enormous kick from this merger sends the newborn black hole rocketing outward at speeds over 2 million miles per hour, fast enough to escape its home galaxy entirely. Other rogue black holes might be the remnants of ancient, failed galaxies, their stars stripped away by tidal forces long ago, leaving only the dark heart behind. The terrifying thing about these drifters, we'd likely only notice one if it passed through our solar system. Imagine Jupiter's orbit suddenly thrown into chaos, its path twisting unnaturally as an unseen mass tugs at it. Or worse, Earth's orbit stretching and warping as temperatures swing wildly between extremes. By the time astronomers pieced together the cause, a rogue black hole could already be halfway through ripping our planetary system apart. Yet the universe has given us a few clues to their existence. Some stars move at impossible speeds, as if shoved by an unseen hand. Others mysteriously brighten in ways that suggest their light is being lensed by a dense, invisible object passing between them and Earth. In 2022, astronomers even spotted what appears to be a rogue black hole over 5,000 light-years away. Its presence revealed only by the way it magnified a background star's light for 300 days as it drifted past. What makes these lone wolves so chilling isn't just their destructive potential, but their unpredictability. A supermassive black hole at the galaxy's center is like a lion in a cage, dangerous but contained. A rogue is a panther in the shadows, unseen until its claws are out. And with millions potentially adrift in our galaxy alone, space becomes less an orderly dance of planets and stars, and more a cosmic minefield where the next invisible killer could be anywhere or heading straight for us. Imagine a cosmic lighthouse so bright it outshines an entire galaxy, not by a little but by 1,000 times. This isn't a star, it's not even a cluster of stars. It's the blinding glare of a quasar, the universe's ultimate power plant, fueled by gravity's most extreme forces. At its heart lies a supermassive black hole, but not the quiet kind lurking in our galactic center. This one is a glutton, devouring matter at a rate that defies comprehension, swallowing the equivalent of a sun's worth of gas, dust, and stars every single year. Here's how the magic happens. As matter spirals toward the black hole's event horizon, it doesn't go quietly. Friction heats the infalling material to hundreds of millions of degrees, turning it into a swirling whirlpool of plasma so energetic, it glows brighter than anything else in the cosmos. The gravitational energy released in this feeding frenzy is so immense, it can't all vanish into the black hole's maw. Instead, it's funneled into twin jets of charged particles blasted outward at nearly the speed of light. These jets stretch across millions of light years, punching through galaxies like cosmic blowtorches. The numbers behind quasars are mind-breaking. A single quasar can emit more light in 1 second than our Sun will produce in its entire 10 billion-year lifetime. Some shine with the luminosity of 100 Milky Ways combined, visible clear across the universe. The first quasars discovered in the 1960s baffled astronomers, pinpricks of light that outshone galaxies 100 times their size. Only later did we realize we were seeing the cores of young galaxies, back when their central black holes were gorging on the rich buffet of the early universe. But quasars aren't just celestial curiosities, they're time capsules. Because light takes time to travel, the most distant quasars we see are snapshots of the universe in its infancy, some flaring to life when the cosmos was less than 1 billion years old. Their existence challenges our understanding of how supermassive black holes could grow so large, so fast. Theories suggest they might have formed from the direct collapse of primordial gas clouds, skipping the star stage entirely and emerging as ready-made monsters in the cosmic dawn. What's truly humbling is that these blazing beacons are all but extinct in today's universe. The era of quasars peaked billions of years ago when galaxies were packed closer together and black holes had endless fuel to consume. Now, most supermassive black holes are dormant, their feasts reduced to a trickle, but their legacy lives on literally. The heavy elements forged in their fiery disks now float through space, part of the raw material for new stars, planets, and even life. Quasars prove something astonishing. Even in destruction, gravity creates. The same force that crushes stars into oblivion also powers the universe's most brilliant lights, stitching together the cosmic cycle of death and rebirth. Every time we spot one of these distant giants, we're glimpsing the universe at its most violently creative, a reminder that darkness and light are two sides of gravity's infinite coin. There's a special kind of cosmic violence reserved for stars that wander too close to a black hole's hungry grasp, a fate so brutal it makes supernova look tame by comparison. When a star crosses the invisible line where a black hole's tidal forces overpower its own gravity, the star doesn't just die, it's dismantled. Imagine a galactic shredder, twisting and stretching the star until it surrenders to gravity's relentless pull, transforming into a luminous ribbon of superheated plasma. Astronomers call these cataclysms tidal disruption events, and they're among the most dramatic light shows in the universe. The process begins when a star, often one roughly the size of our Sun, strays within what's known as the Roche limit. This is the point where the black hole's gravity becomes so differentially strong that it overcomes the star's self-gravity, the force that normally holds it together. The side of the star closest to the black hole feels a vastly stronger pull than the far side, creating an irresistible stretching effect. Within hours, the star is warped into an elongated strand like taffy in the hands of a giant. Then, as internal pressures and heating skyrocket, the star loses cohesion entirely, exploding outward in a brilliant arc of debris. But the horror doesn't end there. The remnants of the star don't just vanish into the black hole all at once. Instead, they spiral inward, forming a swirling disk of glowing matter that heats up to millions of degrees, emitting intense X-rays and ultraviolet light. This accretion disk shines with the energy of billions of stars, sometimes outshining the entire host galaxy for months. And here's the twist: not all the stellar material gets consumed. Some of it gets hurled back into space in colossal jets, propelled by magnetic fields and leftover rotational energy. a final, defiant eruption before the black hole claims its meal. We've actually witnessed this grisly process in action. In 2019, astronomers spotted a tidal disruption event nicknamed the Taffy Tornado, where a supermassive black hole shredded a star about 675 million light-years away. Over weeks, telescopes watched as the star's remnants twisted into a luminous spiral, stretching across trillions of miles before vanishing into the void. These events aren't just spectacles, they're cosmic laboratories. By studying them, scientists can measure black hole masses, test gravitational theories, and even trace how elements forged in the star's death throes get scattered into space. What's truly humbling is the scale of destruction. A single tidal disruption event can release more energy than the Sun will emit in its entire 10 billion-year lifespan. And yet, despite their ferocity, these events are delicate ballets of physics. The way a star tears apart, the timing of its bright flare, the structure of its debris, all of it depends on the star's composition, the black hole's spin, and even the angle of approach. It's a reminder that in the universe's most violent moments, there's still an eerie precision, a beauty in the breakdown. So the next time you look up at the night sky, remember, somewhere out there, a star might be meeting its end not with a bang, but with a scream stretched thin across the infinite darkness, becoming both victim and illuminator of the black hole's insatiable appetite. Somewhere in the depths of intergalactic space, an invisible behemoth is tugging at our entire galactic neighborhood with a force so immense, it overrides the expansion of the universe itself. Astronomers call it the Great Attractor, a mysterious gravitational anomaly located roughly 250 million light-years away, pulling thousands of galaxies, including our Milky Way, toward it at over 14 million miles per hour. This isn't just a curiosity, it's a full-scale cosmic rebellion against the expected flow of the cosmos, hinting at gravitational forces beyond our current understanding. Picture the universe as a vast river with galaxies drifting apart on the current of cosmic expansion. Now imagine a hidden whirlpool in that river, dragging everything toward its center against the natural flow. That's the Great Attractor's effect. Despite its power, we can't see what's causing it. Our view from Earth is blocked by the dense plane of the Milky Way, a region so packed with gas and dust it's like trying to peer through a frosted window. What little we've glimpsed behind this zone of avoidance reveals an even deeper mystery. The Great Attractor might be just the tip of a colossal structure known as the Laniakea supercluster, a web of galaxies spanning 500 million light-years. Here's where it gets stranger. The Great Attractor's pull isn't the end of the story. Beyond it lies something even more massive, the Shapley supercluster, a gargantuan assembly of galaxies whose combined gravity might be amplifying the Great Attractor's tug. It's as if we're caught in a celestial tug of war between unseen giants, with our local galaxies as the rope. This hierarchy of gravitational influence from individual galaxies to superclusters reveals a hidden architecture to the universe where gravity's reach extends far beyond what's visible. The true nature of the Great Attractor challenges our models of cosmic structure. Normal matter, stars, gas, black holes can't fully account for its gravitational grip. Dark matter, the invisible scaffolding of the universe, likely plays a starring role, woven into dense knots that anchor these vast flows of galaxies. But even that might not explain everything. Some theorists speculate about exotic phenomena like primordial defects in space-time or residual imprints from the Big Bang itself, adding layers to the mystery. What's certain is this: the Great Attractor reminds us how much we don't know. Every time we map its influence, we're essentially tracing the fingerprints of the unseen, a cosmic detective story where gravity is both the clue and the culprit. And as our telescopes pierce deeper through the Milky Way's veil, we might soon uncover whether this gravitational enigma is a destination, a waypoint, or just one piece of an even larger puzzle lurking in the darkness. Deep in the night sky, galaxies spin too fast, so fast that by all rights they should tear themselves apart. The stars on their outer edges whip around at speeds that defy the laws of motion, held in place by something we can't see. This cosmic glue is dark matter, an invisible substance that outweighs all the stars, planets, and gas in the universe by 5 to 1. It doesn't glow, reflect, or absorb light, yet its gravitational grip binds galaxies together, sculpts the cosmic web, and controls the fate of everything we can see. Think of a merry-go-round spinning wildly with children clinging to the edges. Now imagine most of the weight isn't in the visible platform or the kids. It's in unseen hands gripping the outer bars, adding enough pull to keep everyone from flying off. That's dark matter's role in a galaxy. Without it, the Milky Way's outer stars would escape into the void and galaxy clusters. The universe's largest structures would unravel like yarn in the wind. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed galaxies in the Coma cluster moving as if bound by 10 times more mass than anyone could account for. He called it Dunkel Materie, dark matter, a label that stuck even as the mystery deepened. What makes dark matter so bizarre is how it doesn't behave. Unlike normal matter, it doesn't clump into planets or stars. It doesn't collide with itself or emit radiation. It's a cosmic ghost detectable only through its gravity. The way its mass bends light around galaxies, a phenomenon called weak gravitational lensing, or how it sculpts the delicate filaments of the cosmic web, where galaxies align like beads on invisible strings. The Bullet cluster offers the most striking proof. Two galaxy clusters collided, their visible gas crashing and heating in the center, while their dark matter, revealed by lensing maps, sailed right through unfazed. Yet for all its dominance, we still don't know what dark matter is. Is it a sea of undiscovered particles, like WIMP weakly interacting massive particles, or primordial black holes forged in the Big Bang's first second? Some theories even suggest gravity itself works differently on cosmic scales, rendering dark matter an illusion, though most evidence points to it being very real. The hunt for answers spans deep underground labs where scientists wait for a dark matter particle to bump into a crystal detector, and space telescopes mapping the distortion of ancient light from the early universe. One thing's certain, dark matter is the universe's silent architect. Every spiral galaxy's graceful arms, every cluster's vast halo, even the paths we'll take between the stars one day, all are drawn by the hand of something we've never seen. It's a humbling reminder that most of the cosmos operates in shadows, and what we call reality might just be the visible fringe of a far stranger universe. Gravity isn't just a force to overcome in spaceflight, it's also a secret weapon. Some of humanity's most daring missions have hijacked the gravitational pull of planets to steal momentum, turning cosmic giants into celestial catapults. This ingenious maneuver, called a gravitational slingshot or gravity assist, works like a cosmic billiard shot. A spacecraft swings close to a planet, using its gravity to bend its trajectory and fling itself forward at incredible speeds without burning a single drop of fuel. Take NASA Voyager missions, for example. Launched in 1977, these twin explorers had an impossible task: reach the outer solar system with the limited fuel of that era. The solution, a grand tour of planetary gravity wells. Voyager 2 performed one of the most elaborate slingshot dances in history, using Jupiter's gravity to boost its speed toward Saturn, which then hurled it toward Uranus and finally Neptune. Each encounter added thousands of miles per hour to its velocity, like a surfer catching wave after wave. The math behind these maneuvers is breathtakingly precise. A slight misangle a few 100 million miles away, and the spacecraft could miss its target by millions of miles, or worse, spiral into a planet. But how does stealing momentum actually work? Picture a skateboarder rolling toward a moving car. If they grab hold as it passes, the car's motion pulls them forward, accelerating them beyond their initial speed. In space, the planet is the moving car orbiting the Sun at tens of thousands of miles per hour. As the spacecraft approaches from behind, the planet's gravity tugs it forward, transferring a tiny fraction of the planet's orbital energy. A planet loses an imperceptible amount of speed. Jupiter won't miss it, while the spacecraft gains a life-changing kick. The magic lies in the geometry. To maximize the boost, spacecraft aim for a planet's trailing side, the hemisphere facing away from its orbital direction. This ensures they're pulled along the planet's motion like catching a tailwind. The Parker Solar Probe used this trick in reverse, skimming Venus to slow down, shedding speed to dive closer to the Sun than any mission before. Gravity assists aren't just fuel savers, they're time machines. Without them, missions to the outer planets would take decades instead of years. The New Horizons probe reached Pluto in just 9 years thanks to a Jupiter slingshot, shaving 3 years off its trip. Even interstellar probes like Voyager 1 relied on Saturn's gravity to escape the solar system entirely. What's truly poetic is that this technique mirrors nature's own mechanics. Comets and asteroids have been gravity hopping for billions of years, their paths reshaped by chance encounters. Humanity just learned to wield the same cosmic tool, turning planets into allies and gravity from an obstacle into an engine. Every slingshot is a reminder. In space, sometimes the fastest way forward is to let the universe itself give you a push. What if black holes weren't just cosmic giants, but could also exist in sizes smaller than an atom? These theoretical specks of infinite density, called primordial black holes, might be lurking throughout the universe, leftover relics from the Big Bang itself. Picture this, a black hole no larger than a speck of dust, yet packing the mass of a mountain. Its gravitational pull would still be fierce enough to shred atoms apart, creating trails of destruction as it zips through space unseen. Unlike the black holes formed from dying stars, primordial black holes wouldn't need a massive star's collapse to exist. Instead, they could have been born in the chaos of the early universe, when extreme density fluctuations caused pockets of space to collapse directly into black holes. Some might have evaporated instantly due to Hawking radiation, a quantum effect that causes tiny black holes to disintegrate over time. But others, with just enough mass to survive, could still be out there, drifting like invisible landmines through galaxies. The terrifying beauty of these mini-monsters lies in their stealth. A primordial black hole with the mass of an asteroid could pass straight through Earth, leaving only a needle-thin tunnel of destruction in its wake. As it entered, its gravity would pull surrounding matter inward, generating intense radiation bursts before exiting the other side. The damage would be microscopic but deadly, like a cosmic bullet too small to see, yet powerful enough to trigger seismic shocks or even puncture a starship's hull. Scientists have searched for them in unexpected places. Some theories suggest primordial black holes could explain dark matter, while others propose they might be the culprits behind strange cosmic explosions with no visible cause. There's even a wild possibility that one might be hiding in our own solar system, an unseen gravitational anomaly tugging at distant objects beyond Pluto. Yet the most mind-bending implication: if they exist, these tiny black holes could be time capsules from the universe's first moments, holding secrets about conditions we can only theorize. Detecting one would revolutionize physics, proving that black holes aren't just endpoints of dying stars, but also fingerprints of creation itself. Until then, they remain one of gravity's most tantalizing what-ifs, a proof that sometimes the smallest things in the cosmos could be the most dangerous. Some of the most violent explosions in the universe don't come from supernova or black holes. Their gamma-ray bursts, cosmic fireballs so intense, they outshine entire galaxies for a few terrifying seconds. These aren't just random flashes in the dark. They're gravity's final scream, the last desperate signal of a star crushed into oblivion or two neutron stars merging in a cataclysmic embrace. Picture a dying star, its core collapsing under its own weight. As gravity overwhelms the forces holding it together, the star doesn't just implode, it rebounds in a titanic explosion, launching jets of plasma at nearly the speed of light. These jets, focused into narrow beams by magnetic fields hotter than the sun's core, punch through the star's outer layers and blast across space. When one of those beams happens to point at Earth, we see a gamma ray burst, a pulse of radiation so powerful it carries more energy than the sun will emit in its entire 10 billion-year lifetime. All of that compressed into seconds. The scariest part, we've seen what these bursts can do. In 2004, a gamma ray burst halfway across the galaxy, 20,000 light-years away, still managed to disturb Earth's upper atmosphere, temporarily ionizing our ionosphere. If one happened within a few thousand light-years, it could strip away our ozone layer, triggering mass extinctions, and the universe has no shortage of candidates. Long gamma-ray bursts lasting more than 2 seconds come from these collapsing massive stars, but the short bursts lasting less than 2 seconds are even more intriguing. These fleeting flashes are thought to be the death cries of merging neutron stars. When two of these ultra-dense corpses spiral together, their immense gravity crushes them into a black hole in milliseconds. The collision ripples space-time with gravitational waves, while the leftover debris erupts in a kilonova, a firestorm where atoms are forged into gold, platinum, and other heavy elements. But before that, as the neutron stars tear each other apart, they unleash those focused gamma-ray jets. It's like the universe's most destructive smithy. Gravity anvils the stars into oblivion, and the fallout becomes the raw material for new worlds. What makes gamma-ray bursts so fascinating isn't just their power, it's their role as cosmic messengers. They allow us to witness events too distant or obscured for normal telescopes. In 2017, astronomers caught both gravitational waves and gamma rays from the same neutron-star merger, marking the first time we'd observed a cosmic cataclysm in both gravity and light. That single event confirmed theories, measured the universe's expansion, and even revealed how heavy elements spread through space. Yet for all we've learned, gamma-ray bursts remain enigmatic. Some last minutes, others milliseconds. Some are ludicrously bright, others oddly dim. And then there are the dark bursts, events that should produce visible afterglows but don't, as if something's swallowing the light. Whether these quirks stem from black hole spin, magnetic fields, or some undiscovered physics, one thing's clear: where gravity reaches its most extreme, the universe doesn't just whisper. It roars. Right now, the universe is expanding, galaxies racing apart like dots on an inflating balloon. But what if gravity, the quiet force that's been shaping the cosmos since the beginning, ultimately wins? Picture a future where that expansion slows, halts, and then reverses, pulling everything back together in a cosmic rewind. This is the Big Crunch, gravity's ultimate revenge, where the entire universe collapses into a single, unfathomable point, a mirror image of the Big Bang but in reverse. The scenario hinges on a cosmic tug-of-war. Dark energy, the mysterious force driving the universe's accelerating expansion, seems to have the upper hand for now. But if there's enough matter and dark matter in the cosmos, their combined gravitational pull could eventually overcome dark energy's push. Galaxies would begin drifting closer, their light shifting from redshift to blueshift as space itself contracts. Over billions of years, the temperature of the universe would rise, the cosmic microwave background growing hotter until it cooks stars alive. Then, as galaxies merge and black holes collide, the sky would become a blinding forge of colliding matter, hurtling toward a final singularity, a universal black hole swallowing everything that ever was. The irony: this apocalypse might look eerily familiar. Just as the Big Bang began from an infinitely dense point, the Big Crunch could end in one. Some theories even suggest such a collapse might trigger a new Big Bang, birthing another universe in an endless cycle of expansion and contraction. It's a haunting idea, our entire cosmic story, from the first stars to the last black hole, might just be one chapter in an infinite loop, yet the big crunch remains a long shot. Current observations suggest dark energy's grip is too strong, dooming us to an endless, icy expansion instead. But that doesn't make the scenario any less profound. It forces us to confront gravity's quiet persistence, the way it patiently weaves the universe together, even as other forces try to tear it apart. Whether the cosmos ends in fire or ice, one truth remains: gravity writes the final sentence. Ever wish you could take a shortcut across the universe? According to Einstein's equations, gravity might have already built the tunnel's cosmic backdoors called wormholes, where space-time folds like a piece of paper, linking distant points in an instant. Picture this: a black hole's crushing gravity punches a hole through the fabric of reality, while a white hole, its theoretical opposite, spews matter out the other side, creating a bridge between them. These aren't just sci-fi fantasies. The math checks out. Wormholes, also known as Einstein-Rosen bridges, emerge as valid solutions to general relativity, suggesting that under the right conditions, space-time could stitch itself into a traversable passage. But here's the catch: keeping a wormhole stable requires something stranger than fiction: exotic matter with negative energy. Normal matter always attracts, bending space-time inward like a weight on a trampoline. Negative energy would do the opposite, propping the wormhole's throat open like an invisible scaffold, counteracting gravity's instinct to snap it shut. Theoretically, if you could line the tunnel with enough of this phantom material, you might just survive the trip. The problem: nobody's ever found negative energy in nature, and creating it in a lab would demand physics we don't yet understand. Yet wormholes tantalize us for a reason. They're not just shortcuts, they're potential time machines. Step into one end, and you might emerge not just somewhere else, but someone else. According to general relativity, the extreme warping of spacetime near a wormhole's entrance could twist timelines, allowing for closed loops where cause and effect circle back on themselves. Want to witness the dinosaurs? Under the right conditions, a wormhole might let you peek into Earth's past, though getting back home would be another challenge entirely. The universe might already be threaded with these hidden passageways. Some physicists speculate that microscopic wormholes could flicker in and out of existence at the quantum level, woven into the foam of spacetime itself. Others imagine primordial wormholes left over from the Big Bang, stretched to cosmic scales by the universe's expansion. And then there's the wildest idea of all: that black holes we've already detected might secretly be wormhole mouths, their singularities replaced by gateways to distant galaxies or other universes entirely. Of course, the risks are as colossal as the rewards. Even if a stable wormhole existed, entering it would be like threading a needle while blindfolded in a hurricane. One wrong step and the tidal forces could shred atoms. The slightest instability might collapse the tunnel mid-journey, trapping you in an infinite void. And let's not forget the paradoxes. What happens if you step through and meet your past self? The universe might enforce its own version of no free lunches, snapping shut any loophole that threatens causality. But the dream persists. Wormholes represent the ultimate expression of gravity's power, not just to bend space, but to fold it, creating connections where none should exist. They remind us that the universe's rulebook might still have hidden pages, waiting for someone bold enough to turn them. Until then, they linger at the edge of theory and imagination, cosmic maybes, whispering that the longest journeys might someday be the shortest after all. Imagine a star moving so fast, it's not just escaping its galaxy, it's breaking free from gravity's grip entirely, rocketing through intergalactic space at millions of miles per hour. These aren't science fiction. They're hypervelocity stars, cosmic projectiles flung into the void by some of the most extreme gravitational encounters in the universe. And the catapult behind this stellar exodus, a supermassive black hole flexing its gravitational muscles in a celestial game of slingshot. Here's how it happens. When a binary star system, two stars orbiting each other, wanders too close to a galaxy's central black hole, the encounter turns into a gravitational tug-of-war. The black hole's immense pull captures one star, yanking it into a tight orbit, while the other gets violently ejected in the opposite direction, like a stone released from a sling. The energy transfer is so extreme, the ejected star can reach speeds exceeding 1.5 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. That's not just speedy, that's galactic escape velocity. The first hypervelocity star was discovered in 2005, racing away from the Milky Way at over 870,000 miles per hour. Astronomers traced its path backward, and the trail led straight to our galaxy's core, home to Sagittarius, a star, the supermassive black hole lurking in the Milky Way's heart. Since then, dozens of these stellar fugitives have been spotted, each with trajectories pointing to a violent past encounter with a black hole's gravity. But not all hypervelocity stars are born from black hole ejections. Some might be survivors of dwarf galaxies torn apart by the Milky Way's gravity, their stars sent careening like debris from a cosmic collision. Others could be the remnants of supernova explosions in binary systems, where one star's catastrophic death sends its partner flying. Yet the black hole slingshot remains the most dramatic origin story, a testament to gravity's ability to both bind and fling objects with unimaginable force. What makes these stars so fascinating isn't just their speed, it's where they're headed. Most are on one-way trips into the emptiness between galaxies, where they'll drift alone for billions of years, their light fading into the darkness. A few might eventually collide with another galaxy, sparking new stellar formations or even seeding planets with heavy elements forged in their cores. And for astronomers, hypervelocity stars are more than just celestial oddities, they're cosmic breadcrumbs. By studying their paths and compositions, we can map the hidden gravitational landscape of galaxies, including the distribution of dark matter that tugs at them along the way. Think about that for a moment. A star born in the crowded heart of a galaxy becomes a solitary wanderer because gravity, the same force that holds galaxies together, decides to hurl it into the void. It's a reminder that in the universe's grand arena, even the most predictable forces can turn into chaos engines, launching stars on journeys with no return. Here's a cosmic mystery that's keeping astrophysicists up at night. Why can't we agree on how fast the universe is expanding? It's called the Hubble tension, and it's not just some academic debate. This discrepancy threatens to unravel our understanding of gravity, dark energy, and the very fabric of the cosmos. On one side, we have meticulous measurements of nearby galaxies and supernova, pointing to an expansion rate of about 73 kilometers per second per megaparsec. On the other, observations of the cosmic microwave background, the afterglow of the Big Bang, suggest a slower rate, around 67. That gap might sound small, but in the precise world of cosmology, it's a chasm. Either we're missing something fundamental about gravity, or the universe is playing by rules we haven't discovered yet. The heart of the problem lies in how we measure cosmic distances. For nearby galaxies, astronomers rely on standard candles, objects with known brightness, like certain types of supernova or pulsating stars called cepheids. By comparing their apparent brightness to their true luminosity, we can calculate how far away they are and thus how fast space is stretching between us and them. This local measurement gives us that higher expansion rate, but when we look at the ancient light from the early universe, the story changes. The Planck satellite's ultra-detailed map of the cosmic microwave background allows us to extrapolate the expansion rate based on the universe's infancy, assuming our models of gravity and dark energy are correct. Those calculations land us squarely in the slower camp. So who's wrong, or more intriguingly, what if nobody's wrong? Some theorists suggest dark energy, the mysterious force accelerating the universe's expansion, might not be constant. Maybe it's evolving, growing stronger over time in a way we haven't accounted for. Others propose that gravity itself behaves differently on cosmic scales, bending space in ways Einstein's equations didn't predict. There's even a wild card. What if our local region of the universe sits in a peculiar bubble of lower density, making nearby expansion seem faster than it truly is across the cosmos? The implications are staggering. If the Hubble tension points to new physics, we might be on the brink of rewriting the rules of the universe. Modified gravity theories, exotic dark energy models, even unseen dimensions, all are back on the table. Every time astronomers refine their measurements with new tools like the James Webb Space Telescope, the discrepancy stubbornly persists, deepening the mystery. It's as if the cosmos is teasing us, dangling clues just out of reach. What makes this puzzle so thrilling is its scale. We're not arguing over details, we're confronting the possibility that gravity, the force we thought we knew so well, has secrets left to reveal. Whether the answer lies in hidden cosmic ingredients, flaws in our measurements, or something entirely unexpected, one thing's certain: the Hubble tension isn't just a gap in data. It's a doorway to discovery, waiting for someone or something to turn the handle. There's something lurking in the cosmos that makes black holes seem almost tame neutron stars with a twist so extreme. They don't just crush matter, they twist the very laws of physics into knots. Meet magnetars, the universe's ultimate fusion of gravity and magnetism, where a star's corpse becomes a laboratory for forces beyond imagination. These aren't your average neutron stars. They're cosmic monsters with magnetic fields so powerful, they could strip the data from every credit card on Earth from halfway across the solar system. Picture the aftermath of a supernova, a star collapsing into a sphere no wider than Manhattan, but packing the mass of 2 suns. That alone would make it one of the densest objects in existence, where a single teaspoon of material weighs 1 billion tons. But magnetars take it further. Their magnetic fields are 1,000 trillion times stronger than Earth's, so intense they actually warp the structure of atoms themselves. Electrons, normally whizzing around nuclei in orderly orbits, are forced into narrow, cigar-shaped paths. Even the vacuum of space around a magnetar isn't safe. It becomes birefringent, meaning light passing through splits into 2 paths like a cosmic prism, an effect predicted by quantum theory but never seen anywhere else. The violence doesn't stop there. Magnetars occasionally unleash starquakes, sudden cracks in their ultra-rigid crusts, only a few centimeters thick but harder than diamond. When these crusts shift under the strain of unimaginable magnetic forces, the resulting energy release can produce bursts of gamma rays and X-rays bright enough to outshine every star in the Milky Way combined. In 2004, a magnetar 50,000 light-years away flared so powerfully, it temporarily ionized Earth's upper atmosphere even though it was halfway across the galaxy. What's truly mind-bending is how magnetars form. Most neutron stars spin rapidly at birth, but magnetars are thought to begin as the fastest rotators of all, spinning hundreds of times per second. This dizzying motion, combined with a dynamo of superheated, electrically conductive material in their cores, amplifies their magnetic fields to ludicrous levels. Over time, their rotation slows as they bleed energy into space, but their magnetism lingers, a ghost of their violent youth. Then there's the ultimate question: what happens if you get too close? The answer is a nightmare beyond physics. A magnetar's gravity would flatten you instantly, but its magnetic field would do something even stranger. At a distance of 600 miles, the field strength would scramble your nervous system, inducing electrical currents strong enough to override the signals in your muscles and neurons. You wouldn't just die, you'd lose control of your body before gravity even got to work. Yet for all their terrifying power, magnetars might hold clues to some of the universe's biggest mysteries. Their extreme conditions simulate physics we can't replicate on Earth, offering glimpses into how matter behaves under pressures and fields beyond laboratory limits. Some researchers even speculate that magnetars could be behind certain fast radio bursts, those mysterious, milliseconds-long blasts of cosmic static that have puzzled astronomers for years. In the end, magnetars are a reminder that gravity isn't the only force that shapes the cosmos. When it teams up with magnetism at these extremes, the universe becomes a place where the rules we know bend and sometimes shatter entirely. Where does Earth end and space begin? The answer lies at an invisible border called the Kármán line, a razor-thin boundary 100 kilometers above sea level where the rules of flight give way to the laws of orbital mechanics. It's not some arbitrary line on a map. This is the point where our planet's grip loosens just enough for satellites to glide freely, where gravity's pull meets the fierce independence of objects moving at orbital speeds. Reaching this altitude doesn't mean gravity disappears. Far from it. Earth's gravitational force here is still about 90% of what we feel on the surface. But something crucial changes. To stay airborne at this height, an object would need to fly so fast, around 7.8 kilometers per second, that it enters orbit instead. Wings become useless, lift transforms into momentum. That's why the Kármán line is more than a technicality. It's the moment aerodynamics bows to celestial physics, where flying becomes falling with style, a style so elegant you miss the ground entirely. The concept was born from necessity. In the 1950s, aerospace engineer Theodor von Kármán calculated this boundary as the altitude where traditional aircraft could no longer rely on air for lift. Above it, the atmosphere thins to near nothingness, forcing vehicles to achieve orbital velocity to avoid plummeting back down. Crossing this line means trading airplane wings for the curved geometry of spaceflight, where speed and gravity perform an endless balancing act. Yet this cosmic starting line is surprisingly contentious. Some organizations like NASA and the U.S. military set space's edge at 80 kilometers, where the mesosphere gives way to the ionosphere and re-entering spacecraft begin glowing from atmospheric friction. Others argue for higher altitudes up to 160 kilometers, where satellites can complete at least one full orbit before succumbing to drag. But the Kármán line's 100-kilometer standard holds a unique elegance. It's where physics flips the script, turning flight from a battle against gravity into a dance with it. Think of it like this: below the line, you're fighting gravity with every liter of fuel burned. Above it, you're harnessing gravity's curve, letting momentum and planetary pull conspire to keep you aloft. That's why rockets don't just aim to reach space, they aim to stay there, accelerating sideways fast enough to turn Earth's gravity from an anchor into a tether. The Kármán line isn't just a technical milestone. It's a testament to gravity's dual nature, strong enough to keep our feet planted, yet flexible enough to let us slip its grasp, if only we're bold enough to move at the right speed in the right direction. Every satellite overhead, every crewed spacecraft, even the International Space Station exists because we learned to navigate this delicate transition, where gravity stops being a wall and becomes a doorway. In October 2017, astronomers spotted something truly extraordinary: a strange, cigar-shaped object racing through our solar system at nearly 200,000 miles per hour. This wasn't just another asteroid or comet. Its speed and trajectory revealed a shocking truth. Oumuamua, as it came to be called, was the first confirmed visitor from interstellar space. But what made this cosmic tourist even more fascinating was how the sun's gravity reached out and gave it a dramatic slingshot, altering its path in ways that ignited fierce debates about where it came from and what it really was. As Oumuamua streaked past the sun, something unexpected happened. Instead of following a simple hyperbolic escape trajectory, it accelerated slightly, too much to be explained by gravity alone. This tiny but crucial deviation set off alarm bells in the scientific community. Natural explanations pointed to outgassing, the idea that hidden ices beneath its surface vaporized in the sun's heat, giving it a gentle push like a rocket's thruster. But the lack of any visible coma or tail, typical of comets, left researchers scratching their heads. The mystery deepened when its shape was inferred to be highly elongated, unlike any known asteroid. Some even speculated, though controversially, that it could be an artificial object, a solar sail or probe from another civilization. What's undeniable is the role gravity played in Oumuamua's journey. The sun's immense pull didn't just bend its path, it revealed secrets about its composition and origin. By tracking how it accelerated and tumbled, scientists could map its likely trajectory backward, tracing a path that suggested it had drifted between stars for millions, possibly billions, of years before stumbling into our neighborhood. The fact that we caught it at all was pure cosmic luck, a fleeting snapshot of an object that had traveled farther and longer than anything humans had ever studied up close. The debates surrounding Oumuamua highlight just how much we still don't know about interstellar visitors. Was it a fragment of a shattered planet, a rogue comet that lost its volatiles eons ago? Or something even stranger? Whatever the answer, its brief encounter with our sun's gravity offered a tantalizing glimpse into the vast and dynamic exchanges happening between star systems. If objects like this are common, then our solar system isn't just an island. It's part of an interconnected highway of celestial drifters, each with stories written by the gravity of distant suns. As Oumuamua vanished back into the void, it left behind more questions than answers, proof that even in the dark reaches between stars, gravity is the silent architect of motion, steering wanderers on paths we're only beginning to understand. The Milky Way seems vast until you pull back the cosmic lens, revealing our galaxy as just one thread in a sprawling tapestry of gravity's making. Welcome to the Virgo supercluster, a colossal assembly of galaxies spanning over 100 million light-years, where our local group, the Milky Way, Andromeda, and dozens of smaller galaxies, is just a neighborhood in a metropolis of star cities. This isn't random scatter. Gravity has spent billions of years sculpting this architecture, drawing galaxies into filaments and knots like dew on a spider's web. At the heart of it all looms the Virgo cluster, a gravitational titan packing over 2,000 galaxies into a space just 20 million light-years wide. Its combined mass, mostly dark matter, warps spacetime so profoundly that entire galaxy groups, including ours, are slowly falling toward it at nearly 700 miles per second. This motion isn't a collision course but a dance, as the supercluster's gravity tugs galaxies into orbit around its dense core. Picture a whirlpool with galaxies instead of water, spiraling over eons. What's astonishing is how delicate the balance is. The supercluster's gravity dominates locally, but it's locked in a larger struggle with dark energy, the mysterious force accelerating the universe's expansion. Over time, dark energy may win, tearing apart these intricate structures. Yet for now, the Virgo supercluster stands as a testament to gravity's patience, a slow, relentless force that gathers galaxies into communities, then cities, then supercities, each bound by the same invisible threads. Zoom out further and the pattern repeats. The Virgo supercluster is just one node in the Laniakea supercluster, an even vaster structure that includes hundreds of thousands of galaxies. But here's the humbling truth. These aren't just maps of where matter is. They're records of where gravity has been, tracing the aftermath of tiny fluctuations in the early universe that grew over cosmic time into the web we see today. Every filament, every cluster is a fossil of gravity's quiet, persistent work. This cosmic web isn't static. Galaxies flow along its strands like beads on strings, pulled by the gravitational memory of ancient densities. Even as you read this, Andromeda inches closer to the Milky Way, the Magellanic Clouds trail behind us, and the Virgo cluster's gravity subtly steers it all. The universe isn't just expanding, it's moving, and gravity is the choreographer. So the next time you gaze at the night sky, remember, the stars aren't just points of light. They are signposts in a vast, interconnected network where gravity writes the rules, and every galaxy, from the smallest dwarf to the mightiest cluster, is just following the script. Gravity rules the cosmos with an iron fist, bending space and time itself, yet when we zoom into the smallest scales of reality, its reign suddenly falters. This is the great paradox of quantum gravity, the glaring gap in our understanding of physics. While Einstein's general relativity flawlessly describes gravity as the curvature of spacetime by massive objects, and quantum mechanics governs the bizarre behavior of particles at the atomic level, these two titans of physics refuse to speak the same language. Merging them into a single framework isn't just an academic exercise, it's the key to unlocking the universe's deepest secrets, from the birth of black holes to the very first moments after the Big Bang. Take the singularity at a black hole's core. General relativity predicts an infinitely dense point where spacetime breaks down, but quantum mechanics insists nature abhors infinities. Something must smooth out this mathematical monstrosity, yet no theory yet reconciles how gravity behaves when compressed into volumes smaller than an atom. Even stranger is the fabric of space itself. According to quantum principles, emptiness should teem with virtual particles popping in and out of existence. But where does gravity fit into this microscopic frenzy? Is it carried by hypothetical particles called gravitons, or does spacetime emerge from something more fundamental, like a cosmic quantum foam? The stakes couldn't be higher. Without a theory of quantum gravity, we hit a wall when trying to describe the universe's first trillionth of a second, when all matter and energy were crushed into a space far smaller than a proton. It's like having a detailed map of a continent but no clue how its tectonic plates formed. Competing approaches offer tantalizing clues. String theory suggests gravity unites with other forces via tiny vibrating strings in higher dimensions. Loop quantum gravity proposes spacetime is woven from discrete, indivisible loops. Then there's holographic theory, where our three-dimensional reality might be a projection from a two-dimensional boundary, a cosmic illusion where gravity emerges from quantum information encoded at the edges. Each idea has its triumphs and tribulations. String theory's elegance comes with the caveat of requiring extra dimensions we've never observed. Loop quantum gravity's mathematical robustness struggles to reproduce general relativity's successes on cosmic scales. Meanwhile, experiments to test these theories border on science fiction. Some hunt for gravitons in particle colliders, while others search for quantum jitters in spacetime using lasers so precise they could detect a virus's weight. The most promising clues might come from black holes, where quantum effects near the event horizon could leave faint imprints, cosmic breadcrumbs leading us toward unification. What makes this search so exhilarating isn't just the intellectual challenge, it's the inevitability of surprise. Every previous unification in physics, from electromagnetism to the nuclear forces, revealed phenomena nobody predicted. Quantum gravity likely holds similar revolutions, new particles, unexpected dimensions, or even a radical rewriting of how we perceive time and space. Until then, the disconnect between our greatest theories stands as both an embarrassment and an invitation, a reminder that for all gravity's obvious power, its quantum secrets remain the final boss battle in our quest to decode the universe. Every star faces a cosmic balancing act, a silent war between gravity's crushing grip and the quantum forces fighting to hold it up. But for white dwarfs, the burned-out cores of stars like our Sun, that battle has a breaking point, the Chandrasekhar limit. This critical threshold, roughly 1.4 times the mass of our Sun, marks the line between cosmic stability and catastrophic collapse. Cross it, and even the universe's most stubborn forces can't stop gravity from winning. A white dwarf is already a study in extremes. After a star exhausts its nuclear fuel, it sheds its outer layers, leaving behind a dense Earth-sized core where matter is packed so tightly, a teaspoon would weigh as much as an elephant. Normally, these stellar embers are held up by electron degeneracy pressure, a quantum quirk where electrons, squeezed too close together, rebel against occupying the same state. It's like trying to cram an entire stadium's crowd into an elevator. At some point, the laws of physics simply refuse, but add just a little more mass, say, by siphoning gas from a companion star, and the scales tip. The Chandrasekhar limit, named after astrophysicist Subramanian Chandrasekhar, is the point where gravity overpowers this quantum standoff. Once a white dwarf's mass crosses that threshold, electrons can't push back hard enough. They're forced to merge with protons, forming neutrons in a violent process called neutronization. In seconds, the core collapses, triggering either a titanic supernova explosion or, if enough mass accumulates, a direct plunge into black hole territory. The star's fate hinges on fractions. A white dwarf nudged past 1.4 solar masses becomes a neutron star, while one pushed significantly further might skip the middle stage entirely, imploding straight into a singularity. This limit isn't just theoretical. In 2014, astronomers witnessed a white dwarf in a binary system flirt dangerously close to the Chandrasekhar limit before detonating as a Type Ia supernova, a cosmic benchmark so reliable. We use these explosions to measure distances across the universe. But here's the twist: under extreme conditions like rapid rotation or exotic matter compositions, the limit can stretch. Some white dwarfs might temporarily cheat death by spinning fast enough to distribute their mass outward, like a figure skater extending their arms to slow a spin. Others, laced with strange quarks or other hypothetical particles, could defy expectations entirely. The Chandrasekhar limit is more than a number. It's a cosmic dictator ruling what happens when stars exhaust their fuel. It shapes the universe's recycling program, ensuring some stellar corpses become the neutron stars that power pulsars and magnetars, while others vanish into black holes, locking their secrets behind event horizons. And for astronomers, it's a reminder: even in the cold, dark afterlife of stars, gravity writes the rules, and quantum physics can only hold the line for so long. Every star in the universe wages a silent, endless war, not against other stars, but against itself. Deep in its core, gravity constantly pulls inward, compressing matter with unimaginable force, while radiation pressure, generated by nuclear fusion, pushes outward with equal ferocity. This delicate equilibrium is governed by a fundamental cosmic rule known as the Eddington limit, the point where these opposing forces reach a perfect standoff. Cross it and a star risks tearing itself apart. Stay below it and gravity keeps its crushing grip in check. The Eddington limit isn't just some abstract theory. It's the reason stars don't instantly collapse or explode the moment they ignite. Imagine a star as a cosmic furnace. The hotter it burns, the more intense its radiation pressure becomes, countering gravity's inward pull. British astrophysicist Arthur Eddington calculated the precise balance where outward radiation pressure exactly matches the inward pull of gravity. For a star like our Sun, this equilibrium keeps it stable for billions of years. But push a star's luminosity beyond this critical threshold, and the radiation becomes so fierce it starts blasting away the star's outer layers, effectively preventing the star from growing any more massive. Here's where things get fascinating. The most massive stars flirt dangerously close to this limit, their surfaces constantly on the verge of being ripped away by their own brilliance. Some, like Eta Carinii, a hypergiant over 100 times the Sun's mass, experience violent eruptions where they briefly exceed the Eddington limit, ejecting vast amounts of material into space. These outbursts act as cosmic pressure valves, preventing the star from completely disintegrating under its own radiation. But the Eddington limit doesn't just apply to stars. Supermassive black holes also play by these rules. When they feed on surrounding gas, they can become so luminous that their radiation pushes back against the infalling matter, effectively starving themselves. This self-regulation ensures they don't grow indefinitely, maintaining a cosmic balance between destruction and creation. The beauty of this principle is its universality. Whether it's a newborn star or a voracious black hole, the Eddington limit is gravity's way of enforcing equilibrium, a reminder that even the most violent forces in the universe must obey the delicate laws of physics. Without this cosmic balancing act, stars would either collapse too soon or burn out too fast, leaving the universe far emptier and darker than it is today. Gravity doesn't just hold moons and planets in orbit. It also has a dark side, a line in the cosmic sand where its pull becomes a shredder. This brutal boundary is called the Roche limit, the point where a celestial object strays too close to a planet or star and gets torn apart by tidal forces. Picture a moon drifting inward, its near side feeling a stronger gravitational tug than its far side. That difference stretches the moon like taffy until gravity's grip overpowers the forces holding it together. The result, a cosmic demolition where solid rock and ice surrender to the relentless pull, fragmenting into rings or a scattered debris field. The math behind this destruction is eerily precise. Named after French astronomer Édouard Roche, the limit depends on the densities of both the planet and its doomed satellite, as well as their sizes. For a typical moon orbiting a gas giant like Saturn, the Roche limit usually falls around 2.5 times the planet's radius. Cross that line and even the toughest materials, solid iron, frozen methane, can't withstand the differential pull. This isn't just theory. Saturn's dazzling rings. They're likely the remains of moons or comets that ventured too close and met their demise at the Roche limit, shattered into countless glittering fragments that now dance around the planet in obedient orbits. But here's the twist, not all objects meet the same fate. A small, loosely held together comet might disintegrate far outside the formal Roche limit, while a dense, solid metal asteroid could survive slightly closer. That's why some moons, like Mars's tiny Phobos, are living on borrowed time. Slowly spiraling inward due to tidal friction, Phobos will one day cross the red planet's Roche limit, not to become rings, but to pancake into a debris shower that might eventually rain down onto Mars's surface. Humanity isn't immune to this physics. Every spacecraft venturing near a gas giant must calculate the Roche limit meticulously, lest it suffer the same fate as those ill-fated moons. Even astronauts would face a gruesome end if they descended too close to a planet's tidal forces, their bodies stretched and compressed until biology lost to gravity. Yet the Roche limit isn't just about destruction. It's a sculptor shaping planetary systems. When a moon shatters, its debris can form new rings, feed newborn moons, or even seed atmospheres with fresh material. In a way, gravity's tearing point is also a creation point where old worlds end and new cosmic cycles begin. The universe doesn't waste a single fragment. Even in annihilation, gravity builds. What if everything you see around you, the stars, planets, even your own hands, is nothing more than an illusion, a cosmic mirage projected from the edge of the universe? This isn't science fiction, it's the essence of the holographic principle, one of the most mind-bending ideas in modern physics. At its core, this theory suggests that gravity, the force we feel shaping galaxies and bending light, might not be fundamental at all. Instead, it could emerge from information encoded on a distant, two-dimensional surface, like a shadow cast by a hidden reality. Imagine the universe as a giant movie screen. Everything you experience, the three-dimensional world of depth, movement, and texture, is actually just data being projected from a flat surface at the boundary of space. Black holes offer the most compelling clue. When matter falls into one, it doesn't just vanish. According to quantum mechanics, its information must be preserved, imprinted somehow on the event horizon like ink on a cosmic ledger. The holographic principle takes this a step further, proposing that all the information needed to describe everything inside a black hole or the entire universe could be stored on its two-dimensional surface. The implications are staggering. If true, this means gravity isn't something that exists independently in three-dimensional space. It's more like a side effect emerging from the way information is processed and projected from that lower dimensional boundary. Think of it like the pixels on your phone screen, individually flat, but arranged in a way that creates the illusion of depth and movement. The universe might operate similarly, with gravity being the special effect that makes the projection feel real. This idea didn't spring from nowhere. It grew out of attempts to reconcile quantum mechanics with general relativity, specifically the black hole information paradox. When physicists calculated how much information a region of space could contain, they found a strange mismatch. The maximum possible entropy or information didn't scale with volume as you'd expect, but with surface area. It's as if a library's worth of books could be compressed onto their covers with no loss of content. Critics argue that the holographic principle remains speculative, lacking direct experimental proof. Yet its mathematical elegance is hard to ignore. Some versions of string theory, like AD/CFT correspondence, explicitly describe a universe where higher dimensional gravity emerges from lower dimensional quantum fields. And if future experiments, perhaps with ultra-sensitive gravitational wave detectors or quantum computers, find evidence supporting this, it would rewrite our understanding of reality itself. The most poetic part, this principle doesn't diminish gravity's power. It redefines it. Instead of a force woven into space, gravity becomes a story told at the edges, a collective illusion so convincing that even space-time bends to its narrative. Whether the universe is truly a hologram remains an open question, but the possibility alone forces us to wonder, if gravity is just a projection, what or who is holding the projector? Gravity has spent 14 billion years sculpting the cosmos, pulling galaxies into clusters and weaving the cosmic web, but its ultimate destiny might be its greatest twist of all. As we peer into the distant future, cosmologists grapple with a chilling question. Will gravity emerge as the universe's architect of order or its agent of annihilation? The answer hinges on a cosmic tug-of-war between gravity's relentless pull and dark energy's mysterious push, a battle that could end in one of three spectacular finales. First, consider the Big Freeze, a slow, silent fade into darkness. In this scenario, dark energy's expansion outmuscles gravity's grasp, accelerating galaxies apart until they're lost beyond each other's horizons. Star formation flickers out as gas clouds stretch too thin to collapse. Black holes evaporate via Hawking radiation, leaving behind a frigid void where not even light escapes isolation. The universe doesn't so much end as exhaust itself, reaching absolute zero in a state cosmologists call heat death. It's a poetic irony. Gravity, the force that once built galaxies, becomes a spectator to entropy's victory. But what if dark energy grows stronger over time? Enter the Big Rip, a far more violent finale. Here, the universe's expansion doesn't just accelerate, it spirals out of control, overwhelming gravity's grip on all scales. First, galaxy clusters tear apart, then individual galaxies unravel. Stars are ripped from their orbits, planets torn from their suns, until even atoms are shredded by the relentless stretching of spacetime itself. The final moments would see the fabric of reality disintegrate into a soup of disconnected particles, erased in a flash of phantom energy. Unlike the Big Freeze's slow surrender, the Big Rip is gravity's ultimate humiliation, a force outmatched in its own domain. Then there's the wild card, the Big Crunch. If dark energy weakens or reverses, gravity could rally for a cosmic comeback, pulling everything back into a singularity. Galaxies would collide in a fiery reunion, temperatures soaring as space contracts. The cosmic microwave background, once a cold whisper, would blaze like an oven, cooking the remnants of stars and planets into a primordial plasma. The universe ends as it began, a single, searing point. Some theories even suggest this collapse could trigger a new Big Bang, birthing another universe in an endless cycle. The strangest twist, we don't know which force will win. Current observations favor the Big Freeze, but dark energy remains an enigma, its nature unknown, its future behavior unpredictable. Could quantum fluctuations spawn new universes in the vacuum? Might undiscovered dimensions rewrite the rules? Gravity's final act is still unwritten, a cliffhanger spanning trillions of years. One thing's certain, whether it's a whisper or a scream, the universe's end will be gravity's last, greatest performance, a reminder that even the mightiest forces bow to deeper laws. From the crushing embrace of neutron stars to the space-time warping might of black holes, gravity is the invisible architect behind the universe's most breathtaking spectacles. We've journeyed through 30 mind-bending facts, each revealing how extreme gravity bends light into rings, shreds stars into spaghetti, and even slows time itself to a crawl. Think about the sheer power of a magnet's magnetic field, strong enough to scramble atoms from halfway across the galaxy, or the cosmic precision of gravitational slingshots, turning planets into celestial catapults. Consider the chilling possibility of rogue black holes drifting unseen through space, or the holographic principle hinting that gravity itself might be a shadow cast from the edge of reality. Gravity doesn't just pull, it creates. It's the force behind the gold in your jewelry, forged in neutron star collisions, and the invisible hand sculpting galaxies into vast superclusters. It's the reason some stars become hypervelocity runaways while others collapse into singularities, warping the fabric of existence around them. And yet, for all we've uncovered, gravity remains full of mysteries. Does dark matter's hidden grip hold the answer? Could primordial black holes lurk in our solar system? The universe is still whispering its secrets. Now it's your turn. Which of these gravity-defying facts left you speechless? Was it the time-stopping power of a black hole's event horizon, or the universe's eerie holographic underpinnings? Drop your thoughts in the comments. Let's geek out over the cosmos together. And if you're hungry for more deep dives into space's greatest mysteries, hit that subscribe button. The universe is vast, unexplained, and utterly wild. Let's keep exploring it, one mind-blowing discovery at a time.